The next part of this section, we're looking at the solubility and the common ion effect. The test tube on the left contains a precipitate of silver acetate in water. The solution is saturated, and the silver ions and acetate ions in the solution are in equilibrium with the solid silver acetate. We can see here's our solid silver acetate, there's our precipitate, and we've got some silver ions and some acetate ions. But what would happen if the silver ion concentration is increased, say by adding silver nitrate? So here I'm adding silver and nitrate. Adding an ion that's in common to an equilibrium causes the equilibrium to shift towards the reactants. Our reactants are the solid form. So that tells us that more silver acetate precipitate should form according to Le Chatelier's principle. And adding a common ion to a saturated solution of a salt will lower the salt solubility. If we're lowering the salt solubility, that means that we're going to have more precipitate. Let's look at calculating solubilities in the presence of other ions. The relative solubilities of salts can often be deduced by comparing values of solubility product constants. The larger the KSP value, the more soluble the compound. The importance of the KSP becomes apparent when you consider the solubility of one salt in the solution of another that has the same cation. Direct comparisons of the solubility of two salts on the basis of their KSP values can be made only for salts that have the same cation to anion ratio. This means, for example, that you can directly compare solubilities of 1-to-1 salts like silver halides, silver iodide, silver bromide, silver chloride, looking at those KSP values. Notice this is 10 to the negative 17th, 10 to the negative 13th, 10 to the negative 10th. We are increasing KSP, therefore we're increasing solubility. Similarly, you could compare 1-to-2 ratio salts like lead halides, lead iodide, lead bromide, lead chloride. Notice this is all a 1 lead to 2 anions, and I'm going from -9 to -6 to -5. So again, I'm increasing KSP and increasing solubility. But you cannot directly compare the solubility of a 1-to-1 salt like silver chloride with a 2-to-1 salt like silver chromate. Notice that there's 2 silvers for every 1 chromate as opposed to 1 silver for every 1 chloride, simply by only comparing KSP values. Let's look at this sample problem. If I had solid silver chloride and it's placed in 1 liter of 0.55 molar sodium chloride. So here I have a common ion. I've got chlorides that are common. Silver chloride is being placed in sodium chloride. What mass of silver chloride will dissolve? Well, let's look at silver chloride and write our equilibrium expression. Silver chloride, we know, will dissolve and be in equilibrium with the silver ions and the chloride ions. Again, I initially start with my reactant, but because it's a solid, I can just leave that off. But initially, I have no products normally, right? I've normally put zeros for both of these. But in this case, I am starting with 0.55 molar chloride ions, right? Because NaCl dissociates into sodium ions and chloride ions, and I have 0.55 molar of it. So for chloride, I'm starting with 0.55. Now I'm going to lose reactants and gain products. So at equilibrium, I will have X silver ions and 0.55 plus X chloride ions. Remember way back when I had those plus X's and minus X's? If I take that KSP and I times it by 100, if it's way less than my initial concentration, I can ignore it. So I'm going to then plug my equilibrium values in to my KSP expression. KSP for silver chloride, if we look it up on our cheat sheet, would be 1.8 times 10 to the negative 10, and that's equal to X times 0.55 plus X. Notice that I crossed off the plus X. So to get X by itself, I'm going to divide both sides by 0.55, giving me X, which is my silver concentration. X is also how much of my silver chloride has been dissolved, right? Because I'm starting with a certain amount initial value and I'm losing X when I'm gaining X. So at equilibrium, I'm going to have whatever that initial amount is minus x. So solving for x, while yes, that is my silver concentration, that is also how much of my precipitate will be dissolving. 3.27 times 10 to the negative 10th molarity. And because I have a 1 to 1 to 1 ratio, my silver concentration, we can say, is my silver chloride. The amount of silver chloride that will dissolve is 3.27 times 10 to the negative 10th moles per liter. Now to get it into mass, which is grams per liter, I'm going to take that 3.27 times 10 to the negative 10th and times it by the molar mass. Add up 1 silver and 1 chlorine. I should get 143 grams. That's telling me that I can dissolve 4.7 times 10 to the negative 8th grams in every 1 liter of that silver chloride. And as predicted by Le Chatelier's principle, the solubility of silver chloride in the presence of added chloride is much less than in pure water. I could find that out by simply doing x times x is equal to the KSP, 1.8 times 10 to the negative 10. So if I took the square root of 1.8 times 10 to the negative 10, because that's equal to x squared, x would equal 1.3 times 10 to the negative 5. Notice the difference, 1.3 times 10 to the negative 5 versus 3.27 times 10 to the negative 10. That's a huge difference, much less soluble. Let's do another example. Calculate the solubility of barium sulfate in pure water and in the presence of 0.01 molar of barium nitrate. We're given the KSP for barium sulfate. Pause the video here. Let's look in pure water. I'm going to use x times x is equal to my KSP. So take the square root of both sides and I would get 1 times 10 to the negative 5th moles per liter would dissolve for my barium sulfate. And for the next one, if I'm in the presence of barium nitrate, barium has now an initial concentration. Barium is that common ion. So I initially have no sulfate, but I initially am putting it in a barium nitrate solution. So I have 0.01. Therefore at equilibrium I am 0.01 plus x and x. When I plug this in, if I take that KSP and times it by 100, I am way less than that initial, so I can cross off that plus x. Divide both sides by 0.01, and I would get an x value of 1.1 times 10 to the negative 8. Again, this is much smaller than in pure water. So with the common ion, my solubility is much less. Therefore, two important general ideas. The solubility of a salt will be reduced by the presence of a common ion in accordance with Le Chatelier's principle. We made the approximation that the amount of common ion added to the solution was very large in comparison with the amount of that ion coming from the insoluble salt. And this allowed us to simplify our calculations. This is almost always the case, but you should double check just to make sure that you can drop that plus x or that minus x. And to do that, remember, you take the KSP value, you times it by 100, and you have to make sure that it is less than whatever the initial amount is that you're starting with. Let's look at the effect of basic anions on salt solubility. The next time you're tempted to wash a supposedly insoluble salt down the kitchen or the lab drain, stop and consider the consequences. Many metal ions like lead, chromium, and mercury are toxic in the environment. So even if a so-called insoluble salt of one of these cations does not appear to dissolve, its solubility in water may be greater than you think, in part owing to the possibility that the anion of the salt is a weak base or that the cation is a weak acid. Any salt containing an anion that is the conjugate base of a weak acid will dissolve in water to a greater extent than given by the KSP. Insoluble salts in which the anion is the conjugate base of a weak acid dissolve in strong acids. Let's look at an example here. We have a precipitate of silver chloride, that's the white precipitate, and silver phosphate, which is the yellow. When I add a strong acid, nitric acid, it dissolves the silver phosphate and just leaves the insoluble silver chloride. That basic anion, the phosphate, reacts with acid to give phosphoric acid, but that chloride is too weakly basic to form hydrochloric acid.